Next, let's look at this compounding idea, and we're in situations where we have multiple compoundings per year. So remember, N is the main difference between compound interest and simple interest, and N is the compoundings per year. And it tells us how many times we earn interest during the year. So if the problem says we're earning interest annually, that means we earn interest once a year. So N is 1. Semi-annually would be twice a year, so that would be 2. Quarterly would be 4 times a year, so N would be 4. Monthly is every month, there's 12 months during the year, so that would be 12. Daily, 365 for N. So we just need to pay attention to what type of compounding we have. Usually the word of what type will be right next to the word compounding. So let's look at a couple of examples of this and use the formula to find how much money we're going to have. Problem number 1, Freddie invests $8,000 in an account earning 5.4% interest compounded quarterly. Notice the wording here, compounded quarterly. How much will they have an account after 15 years and how much interest did they earn? Well, compounded quarterly means that we have N equal to 4. So we need to plug the information that's given in this problem into our formula for compound interest. We're going to just carefully look through everything here. P is the starting amount, and it says Freddie invested $8,000, so that would be my starting amount. Times, parentheses, 1 plus, then we have R. Now, R was given as the interest rate of 5.4%, but remember we're going to plug it in as a decimal, 0.054. You move the decimal point 2 places in comparison to the percent. Now we're going to divide that by N. Now N, as we said, because this is quarterly compounding, is 4. Close my parentheses, and then my exponent is going to be that same N, 4, multiplied by the number of years, 15. I mentioned earlier that it is going to make it easier if you calculate that exponent first before you plug the rest of it into the calculator. So this is 8,000 times 1 plus 0.054 over 4 raised to the 60th. 4 times 15 is 60. Now throw this part of the formula entirely into a scientific calculator. So 8,000 times parentheses 1 plus 0.054. The fraction means divided by 4, close the parentheses, and then raise it to the 60th power. If you do that, you should get 17,886, and I'm rounding here 8 cents. We generally round dollar amounts to the nearest cent, which is 2 decimal places. So this is the amount I'm going to have after 15 years, $17,866, $886 rather, and 8 cents. To figure out how much interest we've earned, or Freddie has earned, I should say, the interest is always going to be the amount that we have at the end, my future value, minus what I started with, minus the P. So I have 17,886. I keep wanting to say 866, but it's actually $886.08 minus 8,000 means that we've earned $9,886.08 in interest. That's a good chunk of change. Let's do another example. Yori invests $9,000 in an account earning 6% interest compounded monthly. All right, so now we have a compounded monthly scenario. So that would mean N is 12. So I'll kind of write that in here. N is 12 while I'm thinking about it. How much will she have in the account after 25 years? How much interest will she have earned? Well, we're going to use the same formula, but our starting investment has changed to 9,000. parentheses 1, you must have the 1 in every example, plus the interest rate, 0.06, always write the interest rate as a decimal, divided by n is 12 because we are compounding monthly, raised to the 12 times t, 25. 12 times 25, I want to do that calculation for the exponent first before I throw it all into my calculator. This would be 9,000 plus times 1 plus 0.06 over 12 raised to the 12 times 25 is actually 300. So I'm going to plug a 300 in as the exponent, and that will give me $40,184.73. So after 25 years, Yori's going to have $40,184.73 in that account. The interest that she's earned during those 25 years will be that final amount, that future value of $40,184.73 minus what she started with, $9,000. So her interest that she's earned is actually $31,184.73. Once again, that compounding, especially for a long period of time, in this case 25 years, she earns a lot of interest. The idea that you're earning interest on not just what you started with, but on the interest you've earned along the way makes a big difference, especially when you go out many, many years, that compounding effect. In fact, compound interest is a form of exponential growth. And exponential growth may be hard to see at first, but as you go out many years, you have this extreme effect of really increasing faster and faster. Before I move on away from this formula, I want to point out two things about the formula. We have n involved in two places. One place is with this fraction on the inside of the parentheses. And I want to mention what's happening there. The interest rate is being divided by how many compoundings you have per year. That's because when you earn interest during the year, say 12 times like in the last example, when you earn interest each month, you're not earning the entire annual interest rate of 6% in Yori's case. You're earning a 1/12 of 6%. Okay, so if the annual interest rate is 6%, you earn a 1/12 of that for every month. So you actually have to divide that interest rate by 12 to think about how much you earn each month during those compoundings. The other place where you see n is in the exponent, n times t. That represents how many times you're earning interest altogether. Because if you earn interest 12 times during the year for 25 years, 12 times a year for 25 years is 300 times altogether. So that exponent is telling us the total number of times you earn interest. So there is meaning to what's in this formula and why we have n multiplying t and why we have n dividing the r.